Hi guys, Tan Chen Hao over here, and today I will be talking about higher spins in quantum mechanics. So in this video, we will derive the formula found on Wikipedia for higher spin states. We will also explain the relation between representation theory, Lie groups, Lie algebras, or branches of math, and spin in quantum mechanics. This video covers the mathematical aspect of spin, instead of the experimental history of spin such as the Stern-Gerlach experiment. So this is the Wikipedia page. We will be deriving these three formulas as well a bunch of others, and we will not be deriving these because these are simply the eigenstates of these operators. So these are just numerical, they can be obtained numerically very easily. So we first begin to understand Lie groups and Lie algebras. So briefly speaking, Lie groups are groups with manifold structure. The topology of Lie groups allows us to discuss or define continuity and derivatives, which gives rise to the notion of a tangent space at each element of the Lie group. So for every element G in the Lie group G, we may define a tangent space at that element to be some vector space. There are multiple definitions of tangent spaces, and three of them can be found at this Wikipedia article. The Lie algebra of a Lie group is defined to be the tangent space at the identity element. So that is the tangent space at the identity element, where the identity element is the identity in the group sense. Namely, the Lie algebra is equal to the tangent space of the Lie group at the identity element. A more in-depth introduction to Lie algebra and Lie groups is covered on YouTube in this awesome lecture series. Now for representations of Hilbert spaces, in order to have a quantum theory consistent with certain symmetries, the Hilbert space must be a representation of the symmetry group. So we take the symmetry, we find its corresponding Lie group, and then we assert that the Hilbert space must be a representation of the symmetry group. We then search for the possible Hilbert spaces there are, and those are the possible particles that can arise out of it. In the case of spinors, the symmetry group is SU2, the Lie group. This is an experimental fact that has led to the experimental verification of spinors. It is also worth mentioning that SU2 is a subgroup of some bigger symmetry group of nature. So in this video, we only be narrowing down our focus to the SU2 Lie group, which will give rise to spinors. So what is a representation? A representation of a Lie group on a vector space V is a Lie group homomorphism. We call it big pi from the Lie group G to a general linear invertible transformation on the vector space V. In other words, the representation provides a way for a Lie group element to act upon a vector V in this vector space to produce another vector G of V. So it is a very natural sense of acting upon this action of the Lie group on the vector space. Similarly, we can define the representation of a Lie algebra, and a Lie algebra, it is a linear mapping from the Lie algebra to GLV. This will come in useful soon. So in order to find the Lie group representations of SU2 on the Hilbert space, we seek to find a Lie algebra representation of SU2 on the Hilbert space. Do note the distinction between this is a Lie group and this is the Lie algebra. This is because there is a correspondence between the Lie group representations and Lie algebra representations. Once we find the Lie algebra representations, we can exponentiate it to find Lie group representations. More specifically, if we let G be a Lie group and a Lie algebra correspondingly, if big pi is a finite dimensional representation on the Lie group acting upon a vector space V, then there exists a unique representation small pi acting on the same vector space such that this is hold true, where X is an element of the Lie algebra, namely the big pi, the Lie group representation acted upon this element of a Lie group is an element of a Lie group because it's the exponential of a Lie algebra. So this acted upon this is equals to the exponential of the Lie algebra representation. This representation is given by this formula. So we see that once we have a Lie algebra representation, small pi, we can simply exponentiate it to obtain the Lie group representation, big pi. This will be done so later. So generally, representations are called they are irreducible and reducible representations. Representations are called reducible if it can be decomposed into a direct sum of smaller representations. Remember that representations are mappings to vector spaces. So there's a sense of direct sum in the terms of vector space. So irreducible representations, which as the name suggests, are representations that cannot be reduced. Hence, irreducible representations act as building blocks for higher dimensional representations via the direct sum. Now, this is the topic of addition of angular momentum, and we'll come across Clebsch-Gordon coefficients if we try to construct higher dimensional representations from the building blocks of irreducible representations. This might be covered in another video, although I must say that there are a couple of good videos on YouTube about this. Hence, we seek irreducible representations of SU2. So once we obtain the building blocks, we can build higher dimensional representations. But first of all, we need to find the building blocks. So because the Lie algebra is a vector space with a Lie bracket, we only need to be concerned with the generators of Lie algebra. So the generators, once again, the generators of the Lie algebra are the basis vectors of this vector space. Because by linearity, once you know the basis vectors, once you know how they behave, you can easily, because the representation is linear, once you know the basis vectors, you can find the representation of any general vector because it's just a sum of basis vectors. So for SU2, the generators are this. You might recognize this from quantum mechanics. It is the commutation relation of spin operators. Now, spin operators in quantum mechanics are really just Lie algebra elements, and commutation relations are Lie brackets. So this is familiar. But now we are talking about it in the language of Lie algebras, and this is the Lie bracket. So for every Lie algebra, there exists a Casimir element. For SU2, the Casimir element is this. This is also known in quantum mechanics as the total spin. And S of x, spin of x, spin of y, and spin of z, I'll call these operators the spin of x operator, spin of y operator, spin z operator. They correspond to spin in the following x, y, z directions. And S squared is the total spin, and this makes sense. So the Casimir element, we can check that it commutes with all the generators, namely S spin x, spin y, and spin z, commutes to be 0. And that means we can find an eigenvector that is a simultaneous eigenvector of both S squared and Sz. Now we can begin constructing the Hilbert space. We will show through a few pages that through a simple but tedious process that the irreducible representations of SU2 are labeled by half integers 0, half, 1, 3, over 2, and 2, and so on. So there's a countably infinite number of them, of irreducible representations of SU2. However, so there's countably infinite of them, and they're labeled by integer or half integer. So to begin, we choose spin z to diagonalize our basis eigenstates in without loss of generality, because if we just chose S a spin of x, then spin of y and spin of z, they behave similar because this Lie bracket is symmetric cyclically. So now the eigenstate lambda m has the eigenvalues lambda and m corresponding to the following operators. Now we want to first restrict the values of lambda. Okay, so using this simple algebraic manipulation, we can obtain the fact that lambda is a positive, is greater than or equals to 0. It's a real number that is greater than or equals to 0. Without loss of generality, we can write it as j plus 1, where j is a real number, a positive real number. This will be useful soon. We therefore relabel the eigenvector as j instead of having lambda. So an eigenvector, we label it with j and m. Now we define ladder operators as the following. Do note that the ladder operator is still an element of the Lie algebra because it's a linear combination of the generators. Now we can simply check these commutation relations, and the first one interests us because the first one looks a lot like harmonic oscillators. This gives rise to a ladder of quantum states, or in this case, a ladder of eigenvectors. Now, we check that the following relations are true. Go ahead and pause the video. And that means that when we have Jm as eigenvector, when we act upon it with S plus, the raising operator, we get another eigenvector with eigenvalues j plus 1 for the S squared operator and m plus 1 for the spin z operator. Similarly, S minus, the lowering operator, would lower the eigenvalue of sz by 1. Now we can show this is true by expanding it, and that means that the value of m is bounded by j and minus j. The absolute value of m is less than or equal to j. This places bounds on the ladder, upper bound and lower bounds, because previously we could raise the value of m, lower the value of m, but we didn't have any restriction on how big or small m can go. But now we do. Now we say that it's restricted between is at most restricted between, or at least restricted between, minus j and j. However, j can still take any value, any real positive value, because we have not placed restrictions on j yet. We will soon do so. However, before we do that, let's check that what the values of m can take. Namely, we are going to show that m, we're going to show that m can reach j and minus j, because this over here just tells us m cannot go beyond j and minus j, but it does not guarantee that m can reach j or minus j. To do so, let's restrict. Let's assume that there's a m max be eigenvector with the largest possible m value. Then we raise it by 1, it must give the 0 vector. Plugging it into this equation, we get this relation, which yields mx equals to j. Via a similar procedure, which namely m minimum, and then lowering it, we get m minimum equals to minus j. This tells us that m not only is bounded, but it can not only is m bounded by j and minus j, but m can in fact reach j and minus j. Now let's proceed to restrict j to the half integers. So to constrain the values of j, we consider a natural number p, and the highest eigenvector is jj. We lower it p times to obtain this j minus p. Now let p max be the maximum value of p such that it is not completely gone, and hence if we do it one more time to this eigenvector, then it will be annihilated by the definition here of maximum of value of p. Now since we know that j minus j is annihilated, then that means that j minus p max equals to minus j, because s, the lowering operator s minus, is invertible, acts on the vector space. So these two vectors must be identical, so they must be labeled by the same index. And that means that 2j equals to p max equals to a natural number. That means j can only take half the natural numbers. So namely 0, 1 over 2, 2 over 2, 3 over 2, 4 over 2, and so on. So j can take any natural number divided by 2. And therefore, we arrive at the following set of irreducible representations of SU2. Namely, for the following spin j representation, I list the basis vectors on the right. For spin 0, we have the m equals to 0 state only. For spin half, we have the m equals to minus half and m equals to half state. For spin 1, I have the m equals to minus 1, 0, and 1 state. and so on. And how the Lie algebra elements act upon these basis vectors is important as well. So we know that the spin z component, the spin z operator, it acts upon the eigenvector. Eigenvector is the eigenvector of spin z operator, so it just leaves a constant here. However, raising and lowering operators change the eigenvector, and there's this prefactor in front of it as well. Now, from the definition previously, we can also express spin x and spin y in terms of raising and lowering operators. This will be useful later. Now, for each possible spin j representation, let's say we have spin 1, the basis vectors, which is -1, 0, and 1, they span the entire Hilbert space. In other words, a spin j quantum state is a linear combination of basis vectors -j plus half. I'm so sorry, this is supposed to be -j plus 1, j dot 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 all the way j minus 1 to j. So this will be a total of 2j plus 1 basis vectors. Hence, the Hilbert space, spin j Hilbert space is a 2j plus 1 dimensional representation of the SU2 Lie algebra. That is what spin is in quantum mechanics. We now go on to calculate the matrix representation of spin operators. We do so for spin half and spin 1 systems because higher spins are generally more tedious, and as long as you know how to do it, you should be able to do it with enough time. So in this video, I'll only cover spin half and spin 1 to illustrate the techniques. So for spin half, in order to, so right now, essentially we have these basis vectors, am I right? And this is a finite dimensional vector space. So that means we can represent linear operators as matrices. So to do so, we need to write the basis vectors as column vectors. So we identify the m equals to half as this column vector and m equals to minus half as this column vector. Then we take the action of certain linear operators, namely the sz, spin, the raising and lowering operator, and we see how they act upon this eigenbasis vectors. And from there, we can construct a matrix representation of the linear operators. So for spin z direction is this. For the raising operator, I'll go through this in detail. So when we take the raising operator, we act upon the 1, 0 vector. What is the 1, 0 vector? The 1, 0 vector is the m equals to half eigenvector. M equals to half eigenvector, when we raise it, it gets annihilated because there's no higher value of m. So it's the 0, 0 vector. For the m equals to minus half vector corresponding to 0, 1 column vector, as raising operator acted upon it, it gives you the m equals to half vector, eigenvector, which is the 1, 0 column vector. So this is true. So this is true. Hence, if we take a look at these two, and we consider if we take a look at these two, we arrive at the following matrix representation of the raising operator. Remember that this is dependent on the basis. And what basis have we chosen? We have chosen the basis of eigenstates of the spin z operator, clearly seen here by the diagonal matrix of the spin z operator. So if we chose something else as the basis, then it will change. So for now that we have, we can do a similar procedure for the lowering operator, and then we arrive at the spin x operator and the spin y operator, because it's simply half times, spin x is simply half times s plus s minus, spin y is minus I over 2 times s plus minus s minus. So these are the three spin operators in the matrix representation, and we're talking about spin half system. So in the spin half representation of the SU2 Lie algebra, we choose basis vectors to be the eigenvectors of the spin Z operator. And once we have chosen the basis vectors, we can represent the spin operators in a matrix as according to how they act upon the basis vectors. So to find the eigenstates of the spin operators in terms of the basis of the spin Z operator, we simply need to find the eigenvectors of these matrices, these 2 by 2 matrices. This is really simple, so I will not cover it in detail, but Wikipedia does show a list of list of them. Let me just find it real quick. Sorry, I'm just trying to find it for you. Spin, it's under spin. So the eigenvectors are given by these 9 eigenvectors on the right. And you can see that on the left, oh, we haven't covered spin 1, but you see that later it matches our calculation. So these are the eigenvectors. Okay, let's go back. Okay, so for spin 1, we use the following column representation, similar to what we did for spin half, and we arrive at the spin Z operator matrix representation. Now we do the same thing. If we apply the raising operator to the higher state, we get 0. If we apply the raising operator to the m equals to 0 state, we get m equals to 1 state with a prefactor. And if we apply the raising operator, oh my gosh, there's a huge fly on my table right now, but I'll just try to remain calm. Okay, sorry. Oh my god, okay, I'm kind of scared. Okay, anyway, okay, so sorry, I will remain calm. So if we apply the raising operator to the m equals to -1 eigenvector, then we get the m equals to 0 eigenvector with the prefactor. So from this we can obtain the matrix representation of the raising operator in terms of the basis vectors like this, and similarly can be done for the lowering operators. This gives us the matrix representation of the spin x and spin y operators, and this is a summary of the results. You can see that this agrees with the Wikipedia page, and similarly the eigenvectors can be easily found by numerical calculation of the matrices eigenvectors. So I'll not be covering that. So lastly, let's talk about exponentiating the Lie algebras to obtain Lie groups. Now recall that our original goal was to find the Lie group representations on the Hilbert space. Now, so because a general Lie algebra element can be written as this, where n hat is a unit vector, then phi is a scaling factor, and s is the 3 basis vectors. So this is basically what I'm trying to say here is that remember that the Lie algebra is a vector space, right? So a general vector in this vector space, in this Lie algebra vector space, can be written in terms of its basis vectors. And how do we do so? We do so by coefficients, right? So the coefficients are phi nx, phi ny, and phi nz. And the basis vectors are spin x, spin y, and spin z. Now, spin x and spin y and spin z, they are in the abstract sense. Sorry. Yeah, so they're in the abstract sense, meaning sx and spin x and spin y and spin z, the exact value of them, or the exact matrix that represents spin x and spin y and spin z, depends on the spin j representation we choose. But more generally, we can still write it like that because they are defined in the abstract sense of their Lie bracket and stuff. So we can exponentiate this to obtain Lie group elements. And that's how we obtain representations of the Lie groups on the Hilbert space. Now for spin half, there's a very nice formula for it. It's the Euler formula for Pauli matrices, and it's given as such. So we have hence obtained, we exponentiate this. This is the, in general, this is the Lie group representation of SU2 on the Hilbert space, and we have hence finished talking about spin in quantum mechanics. I hope you have enjoyed this video. If you do, please leave a like and subscribe. Have a nice day.